Well, I'm back, guys. There's a video I've been meaning to do for a while, and looks like a lot of interesting stuff here, doesn't it? What this is we're going to talk about Kirchhoff's laws or rules on circuit analysis. Now, Robert Kirchhoff was a physicist and dabbled with a strong interest in electronics and electricity, and he developed two laws or rules for circuit analysis. Now, why would you be interested in this? Well, primarily it helps you, well, if you was to design a voltage divider for something, or try to figure out one as far as a current going through it, you don't have a schematic, resistors are burned up in it, you need to figure out what they are. Either case, Kirchhoff's laws come in very handy in the design of it, along with a few other just learning about circuits or understanding both the current and voltage drops through any particular circuit. Now, what I've drawn out here is a real simple circuit. We'll look at actually two, and I went ahead and done the math and everything. We'll go through it, but let's state both of his laws right off the bat. His first law is known as the Junction Law or Node Law, dealing with current. It's really dealing with the sums of currents. And a junction or node is wherever you have three wires or more breaking off at a point. Now, in the very basis, simplest terms, what he stated in his law was that the algebraic sums of all the currents going into a junction will add up to zero. Meaning, basically, if you got current coming in to a junction, one coming this way and one coming this way, and leaving that junction, if you add them up algebraically, they will add up to zero. Now, the other rule or law is called the loop law, and it deals with voltage drops. You establish a loop like this purple here and this outer loop. It states that the algebraic sum of all the voltages, the voltage drops in that loop, will add up to zero. Okay, what does that mean? Well, basically this circuit here, since we only have one supply, we're not really going to concern ourselves a whole lot about the junction rule as much as the loop rule. And I established, you can establish the loops any way you want. I established two loops here. One's here, so we're going through the battery, this resistor, and this resistor. The other one is the entire outside section, so from the battery through this, and this resistor back to the battery. The first one we write out using the loop law, which means that the algebraic sum of all the drops, all the voltages, must add up to zero. So we start off with, in this 10-volt battery, so we start off with 10 volts here. We're going to follow through this way. So we take 10 volts, it's positive here, so we have plus 10. We come to here, we have 2 ohms with a current that's unknown. So it's I1. I just labeled it I1. You can label it anything you want, but it's a current. And according to Ohm's law, resistance times current gives us voltage. So it's minus 2I1. 2 times I1 will give us that voltage drop. Now, I need to talk about convention. If I follow the rule of current traveling from positive to negative, now you can use whichever convention you want. You can go negative to positive also. But in this case, we followed positive to negative. So we leave a positive, we have to hit a negative. Now wires, we assume in any circuit, is basically ideal. In other words, they have no voltage drop on the wire. So they have no resistance. Yeah, I know in reality there's a little bit of drop there, but it's minuscule. It's not really needed to even be figured in. So we go from positive to the first place where we're going to drop voltage, and that'll be a negative. Positive to negative. So we write a negative here, but on the other side, as the current goes through, we come back to a positive, and then we just keep going. We assume, or I'm assuming, that the current's going to go this way and this way. It's going to split here. So then I hit a negative. On the other side it'll be positive, come back to a negative again, positive, back around to negative, positive, back to a negative. Since I'm assuming it's splitting here and it's coming this direction as the arrow, then it'd be a minus to positive, minus, positive. So when we start writing these out, then and adding them up, we'll have positive 10 minus 2I1. Since I don't know the current, I have to put the variable in. Minus, now here we've got I1 minus I2 is our current going through here, which it is. The current that's coming through here is going to be I1 subtract this I2 that's going through here. So I just write it out, I1 minus I2 across a 2 ohm resistor. So Ohm's law again, resistance times current gives voltage drop. So minus 2, I'll put parentheses to keep that quantity together, I1 minus I2. Come down to here, we have a 5 ohm resistor, unknown current, so I1, it's the same current as up here. So it's minus 5 I1, and that all equals 0. To keep in our rule with Kirchhoff. So the algebraic sums of all these, when I would add these all together, they would equal 0. Now we take the outside loop. Again, we start with 10 volts positive minus 2I1 right here minus 3I2. This will be I2 current because this loop here has I2 in it. And it's 3 ohms. Minus 1 ohm I2, same current, minus 5 I1, which is this one down here, equals 0. Now we just go ahead and get rid of the parentheses, and we do some combining of like terms, I1s and I1s and I1s and the I2s. We come out and rewrite it, we get 10 volts minus 9I1, because I got a minus 2I1 here, a minus 2I1 here, and a minus 5I1 here. So this is 2 and 2 is 4, and 5 is 9, gives me minus 9I1. This is minus 2 times a negative I2. Well, the two negatives become a positive times I2. That gives me a plus I2 equals 0. Do the same thing down here, just combine the terms. We come up with 10 volts minus 7I1 minus 4I2. We got 2I1 here and 5I1 here. That gives us 7I1. We have minus 3I1 here and a minus 1I1 gives us minus 4I1. Now, just rewrite it so it's not equal to 0. We get 10 volts equals 9I1 minus I2, and 10 volts equals 7I1 plus 4I2. I have two identical equations, or what they call simultaneous equations, and I have two unknowns, I1 and I2 is my two unknowns. That I have to have two equations to solve for two unknowns. I do have that. So what I'm going to do is add these equations together, but I want to eliminate one of the unknowns. Well, the easiest way is the I2s. All I got to do is multiply this one by 2, which I show here, and that eliminates this right here when I add them together, because this will make this 4 minus 4 plus 4 is 0. When I work it out, it comes out to 30 volts equals 25 I1. So I take 30, divide by my resistance, which is 25, to get my current, and that gives me I1 equals 1.2 amps. Now all I got to do with that is turn around and substitute that back into one of these two equations. I picked this one here, rewrote it, punched this in. I1 is 1.2, so 1.2 times 7 is 8.4. I have 10 volts equals 8.4 volts plus 4 I2. Move this on this side, number to subtract both sides by 8.4. I get 1.6 volts equals 4 I2. Do the division, I get I2 equals 0.4 amps. Now if you want to check yourself on something like this, then all you got to do is take this current and multiply it times the resistance that it goes with, and take this current times the resistance that it goes with, and the center one, subtract the two currents and times that resistance, and you get your voltage drops. Well, this is 2.4 volts. This one's 6 volts. This is 1.6 volts. This is 1.2 volts. And this is 0.4 volts. Now if I run my loop like I had and figured up 2.4 plus 1.6 plus 6 should equal 10 volts, and it does. 1.6 plus 2.4 is 4 plus 6 gives me 10. If I follow the outside loop, then I got the 2.4 plus 1.2, 0.4, and 6 again gives me 10 volts. So it works out, and if I would actually plug those numbers in here, it would come out to 0 then, because they'd all be negative numbers, and because they're subtracting voltage from, they're dropping voltage from the battery. Now if you do something like this and you end up with, and I'll show that in another piece of work I did on paper, I won't draw it on here, but if you would come out with a negative current, you can't have negative current, but if you would come out with a negative current, your answer comes out, say like I1 came out to negative 1.2 amps. All that means is it's correct current level. It's the correct amount of current. The negative just means that the loop was drawn in the wrong direction. So if I drew this loop this way instead of this way, it would have came out at negative 1.2. So if you ever do a problem and work it out and your current comes out negative, you're fine. All it means is that your current's actually going the opposite direction. Now to show you another one, which is the figuring out the direction of current, but as well as figuring out voltage drops and everything in what is known as a Wheatstone Bridge. Wheatstone bridges have been used a lot for very sensitive meters for certain things. They're also bridge circuits are used in pretty much all your, which basically are Wheatstone bridges, all your vintage resistance capacitance comparator bridge testers, the ones that you use that you can also check for leakage, high voltage leakage. These are the like the ICO 950B, Solar, I can't remember their model number, Heathkit makes one. There's several different companies. You've seen mine and stuff. They're based on the Wheatstone Bridge. And I'll see if I can kind of zoom in a little bit on this, just a tad point, and bring this down just a little bit here. Okay, basically we have a Wheatstone Bridge, and that's all it is. You get the diamond shape with resistors, and then you've got a center resistor connecting. These cannot be figured up in your normal parallel series type figuring up of circuits. You literally have to use Kirchhoff laws on these. In this case, we're going to run a 13-volt battery. Most of the resistors except for this one, in fact all the resistors except for this one, are 1 ohm. This one's 2 ohms. There's going to be 3 currents, so I have to have 3 loops to create 3 equations. So my first loop will follow this path. My second loop will go around this path, and the third loop will be inside this area. We have current coming this way. We split here. We have I1, I2 comes down here. I1 splits off, goes I3. This direction it'll be I1 minus I3. So it's I1 subtracting this current here. On this branch here, as I2 comes down, it meets up with I3. So then the current going through here is I2 plus I3. We come back to our battery, it's I1 plus I2. So basically what I did was to make up, okay, loop 1, we have 13 volts plus 13. This is your positive here. Following through, minus I1 times 1 ohm right here, minus I1 minus I3, that quantity, times 1 ohm, it's just this right here, equals 0. The second loop, we'll have our 13 volts, we'll have minus I2, 1 ohm, minus the quantity of I2 plus I3 times 2 ohms, and then plus 13 coming back, equaling 0. Inside this loop, we have no supply voltage. We just have, we look at I1 minus I1 times 1 ohm coming through here, minus I3 times 1 ohm, plus, going opposite direction here, plus I2 times 1 ohm equals 0. Now I can rewrite that as I2 equals I1 plus I3 just by rearranging this and just dropping the 1 ohm out, because everything except for this 2 ohms, everything is just 1, so I can just leave them off. Combining terms and everything, we come out with 13 volts minus 2 I1 plus I3 equals 0. And then we have 13 volts minus 3 I1 minus 5 I3 equals 0. Now, what I also did with this here was not only did I combine the terms, but I also took this here and substituted in as well. But after the substitution and everything, we end up with 13 volts equals 2 I1 minus I3. 13 volts equals 3 I1 plus 5 I3. Now all I got to do is eliminate somebody. Well, I3 is the easiest one to eliminate by multiplying by 5. I do that. I come up with it comes out to 65 volts equals 10 I1 minus 5 I3. Add these two together, I come out 78 volts equals 13 I1. The I3s cancel out because 5 minus 5 is 0. Do the math, 78 divided by 13 gives me I1 of 6 amps. I substitute that back into this one. That ends up giving me the 13 equals 12 minus I3 gives me I3 equals minus 1 amp. Now the 1 amp's correct, but it's negative, because what that really means is the current is not following this direction, it's going this way. So I got the loop wrong direction. So anyway, we come out 1 amp, we plug that back in, we get I2, because we have I1 plus I3 equals I2, that gives us 7 amps. Now if I take and put those combined together, I1 plus I2, and divide it in 13 volts, I can find out what the equivalent resistance of this entire network is. So I do that. I1 is 6, I2 is 7, that gives me 11 amps. It's 13 volts, so 13 divided by 11 gives me 1.2 ohms is what this all equals. And actually it's this loop right here, that loop 3, that's needs to be reversed, not this current flow here. That current flow was actually correct. But anyway, that's what this meant right here. This negative was that this loop, because that's where this actually came from, this loop was going the wrong direction. I had it this way, it needs to go this way, and then it will come out positive. You can't have negative currents. But that's basically how you do, that's the way you do one of these. You just set up your loops, figure up your voltage drops, combine like terms, simplify down, find out what you got to multiply one of the equations, the other equation by a certain number, whatever it takes to get rid of anything left remaining, so that you only have one variable left. Add them together, do your division out to get your current. Just simple Ohm's law, voltage times voltage divided by resistance gives me current. Once you got the current, then you can take and substitute back into one of the equations, get the other current. Once you got that, then you can substitute back in if you need to get a third current if you need to find one. If you got something like this, then you can figure out your effective resistance, what the load that this supply is seeing, by just doing figuring up the current that's going in back to the battery, and doing Ohm's law again. Voltage divided by current or amperage gives me resistance. So this whole thing here really looks like a 1.2 ohm resistor. So anyway, the video is starting to get long, but that's Kirchhoff's laws in a nutshell. If you have any questions, I'll go over some more examples of these. They're not really difficult. They're just a little bit to set up the equations and then figure out how to get the equations simplified. Sometimes can be a little time consuming for people, but once you do that, then you start spotting out what you need to do to finally finish everything out and get your first current, and then you can take that first current and substitute in wherever is the easiest place to substitute it in to find your next current and however many currents you need to find. So I hope that was fairly clear and concise. If you have any questions, just leave them in the comments. I'll be doing a video probably today, the next one on the transformer, and try to get it uploaded also today. I'll probably also do the answer to the question I left and do that video. So far 2 people submitted an answer, and I don't know if I'll get that uploaded today, or I might wait just another day to see if anybody else wants to tackle it. So anyway, be looking forward to it too. So until next time, thank you.